The next thing that I want to prove is that for any vector space V, say, let's let V1, doesn't matter, let's let U and V be vectors. It turns out that the span of U and V is a subspace of V. So in other words, the span is always a subspace. So I want to prove this. And to prove this, we're going to use the subspace test. Subspace test. So what we're going to do is we're going to say, let's pick two values from the span and show that their sum is also in the span. So let's consider, say, A1U plus B1V. This is a V, by the way. And A2U plus B2V. Okay, so let's consider those two vectors. These two vectors are coming from the span of U and V. They're both linear combinations of U and V. And so then we can just check that if we add these together, A1U plus B1V plus A2U plus B2V, turns out that we can add these together, we can associate the U's together, we can factor it out. This is A1 plus A2U plus B1 plus B2V. And so this is in the span of U and V. So it turns out that if you pick any two arbitrary, any two linear combinations of U and V, their sum is also going to be a linear combination of U and V. So in other words, start with any two vectors that you want from the span, and their sum is also in the span. And the final thing that we need to check is we need to look at, so consider some arbitrary element in the span, say AU plus BV, and let's compute K times this vector, K times AU plus BV. And this is going to be KA times U plus KB times V, okay, which is in the span. So this is in the span of the set of vectors U and V. So it turns out that the span satisfies the subspace test. And so it turns out that the span of any set of vectors is always a subspace of V. The proof that we provided here really is only a proof that if you take a span of any two vectors, that it's a subspace. But you can easily adapt this and show that the span of any set of vectors, say V1 to Vn, is a subspace of the set of vectors V, where these vectors V1 to Vn are vectors in V. Okay, so this is going to be an important proposition for us, that the span is a subspace. That's why every step along the way so far when talking about the span, we've always gotten a subspace. That was not a coincidence. It turns out that the span is always a subspace of the underlying vector space V.